Welcome everyone. I hope you're all having a great build. I'm Lee Stott. I'm going to be your moderator for the session. Justin Garrett will be presenting soon on the topic of can polar bears predict climate change. But before we start, I wanted to let you know we're going to be hosting a Q&A with the presenter after the session. So please add your questions to the Q&A section. Can you all please pay attention to the Microsoft Digital Code of Conduct, and we hope you enjoy this session. Over to Justin.
All right, thank you, Lee. So good afternoon, good evening, and good morning to you. As Lee said, I'm Justin Garrett. I'm a principal program manager here at Microsoft. My team focuses on student hackathons and student developer content. So presenting to you today is actually one of the things that I get to do every day in my job, and I love it. And so this is just an honor to begin. We're going to talk about polar bears and computer vision. And really tie those things together in a way that really kind of seeks to think about how do you use technology to really create social impact and to evaluate it and to make a difference in this world. We'll talk about some common careers that one might pursue in this space and how to build your own tech skills as well. And of course, as Lee said, we're going to have plenty of time for Q&A. So let's begin with talking a little about global climate change. And so this data comes from NASA and NOAA. And you might notice in the chart that from 1950 to currently, there's been a substantial change in the overall carbon dioxide level on the planet. Just to kind of orient yourself to the scale of it, this is a chart that measures the Earth's age in hundreds of thousands of years. And so do with that what you will. But if you look at the trend line, certainly, regardless of what you believe about where our trajectory is, you look at that 1950s level and now and you say, there's something that's a little different about this curve. Maybe we as climate scientists, software engineers should explore this a little bit further as well. So, can polar bears help us? Well, I think they can, other than the shameless amount of polar bears pictures that I put into this presentation. And so polar bears are very unique. They live in the frozen Arctic wild, and we'll talk about why that's so important in just a minute. But some fun facts. Their fur is actually not white. It's actually somewhat clear. But because they tend to live in the Arctic and they have a lot of ice around them, their clear fur tends to reflect light, and that makes them look white or lighter to our eyes as well. They're the largest living meat eaters. They can smell food from 10 miles away, walk and swim 60 miles, so they're capable of great distances. But more than anything, they are living right now in a place where the Earth is changing. Maybe this is something that we can explore. It's also kind of difficult for humans to chase after polar bears, especially when most of us are at home right now. But beyond all of the things that are happening exceptionally right now, currently it's always cold there. There's not a lot to eat. And they're rather ferocious as well. So all of this just kind of suggests that we need a technology solution to better understand the habitat and the overall traceability of polar bears. We're going to center our exploration around Cornwallis Island. So this is a small island, relatively speaking, in the Canadian Arctic. And if you look at the map, you'll notice that Cornwallis kind of sits right in the middle of all this different chain of islands. And that kind of makes it unique because it's been known for hundreds of years that polar bears tend to migrate to Cornwallis Island. But on certain years they can get there and other years they can't. And so if we were to build something that kind of is able to measure the number of polar bears that are able to cross the Arctic ice and make it to Cornwallis Island, that might give us some clues over time in a large data set about global climate change. Pretty cool, huh? So how might technology help us track down these polar bears? And it turns out in the last 5 to 10 to 15 years, the technologies that we have now at our disposal has made it a lot easier, to be able to build something like a polar bear tracker. First of all, cameras are available and easy and cheap to deploy. You've got a camera on your phone today or cameras on every one of your devices. You can then hook up that camera to a computer. That computer can be actually quite small, like say like a Raspberry Pi or an Arduino or a small board. But that computer is then capable of collecting data that begins from those cameras. Maybe that data is particular metadata or something that puts that image from the camera in context. We're going to talk about that in a minute too. If that device has internet connectivity, maybe beamed up from a satellite, then we can access that data anywhere in the world. And that's where the Azure cloud as a platform comes in, is if we can access it through the internet, then we can analyze that data in either real time or batches to ultimately allow our climate scientists to use the scientific method and gain new insights. If you're interested in a career around this, this isn't just something that a software engineer does. In fact, a software engineer is an important aspect of a project like this, but so is a climate scientist, and so is a data scientist, or someone that's able to build artificial intelligence models that can predict and track what a polar bear is as well. Let me explain. So we begin our architecture with an image captured. As mentioned, we're going to add some metadata to that image, in this case, latitude and longitude, as well as a date stamp that allows us to kind of infer some basic meaning on where that image came. Once we've gathered that image and that metadata, we need to securely get that to the cloud, and that needs to be in a way that hackers can't access it, and so it needs to have keys and things to make sure that the integrity of the data is preserved. Data scientists often do a lot of cleaning and storing on the data and processing. In this model, we've done all that hard work for you, so we're going to kind of skip that step. But if you're interested in being a data scientist in the future, that is a key step. Oftentimes, 80+% of a project is spent cleaning and storing data. We're going to spend the majority of our time on the polar bear prediction model. And of course, we're going to visualize this over a Cornwallis Island map. Pretty cool. So let's go to the demo. My screen refresh there. All right, and so let's begin with our computer vision model. So I've pre-staged a Azure solution called Custom Vision, customvision.ai if you're following along. And this is a free tool with premium tiers that allows you to build your own AI model without using code. We're going to use some code a little bit later in our solution in Azure, but for now, we're able to build a classification model simply by uploading images and then basically tagging those images or labeling them and classifying them. And so I want to explain classification a little bit for those of you who are less familiar. So really what we're doing here is bucketing different information. So for every image that comes through, this model is going to take that image, and based on my training data, it's going to determine or predict whether that image is a polar bear, is an Arctic fox, or is a walrus. Pretty cool. So I'm going to create a new project, label it with my description, select classification. Of course, you can do all sorts of different other types of models. And in this UX, really all I have to do is click the blue button to begin.
Hey, Justin, we can't see your screen.
Okay, let me go ahead and see if I can fix that. All right, resharing. Desktop 1. Okay, double checking again. Can you see the Custom Vision UX?
Yes, it's up. Thank you.
Okay, great. Switching screens. Thank you. So I am in the Custom Vision UX of Azure here, and I click to add images. And so what I'm going to do is I'm going to load up my training images. So I'll start with Arctic fox, and I'll select all, and basically just uploading 130 images of Arctic foxes. And I'm going to tag that Arctic fox. Pay special attention to how you tag things, because if you call those in code later, you need to use the exact string. Click upload. And so basically my 130 images of foxes are now being uploaded. And I'm going to repeat this step for my other images. Let's try our walrus now. Select all images. Tag these walrus, 138 images. While it's doing that, you can admire some of the cute foxes that are on the screen. You can recognize that these images are indeed Arctic foxes. And then finally, I'm going to upload polar bear images. Again, this is my training data, so none of these pictures are what are actually going to be what my cameras ultimately look at. Upload 140 polar bear pictures. And once I've completed this, really all I need to do for my classification model is click the green train button. And basically, Custom Vision does the work for me. So in the interest of time, I'm going to switch to a completed model. Usually training only takes a few moments, but just for the sake of time, this is the output of my model. And you can see there are really 3 different types of evaluating the different type of success of my models: precision, recall, and what's called average precision. So basically, precision is a measure of the true positives that I have when I was trying to determine whether or not it was a polar bear. I can kind of test this a little bit. So let's use a quick test here. And I'm going to upload an image. And this time I am not going to use an image that was in my training data. That's very, very important. So I'm picking an image that was not one of the images that I stored, and I'm going to try to have my model guess to see if that picture is in fact a polar bear. So I go ahead and upload that. You can see it's sitting here, and my prediction model says polar bear probability 100%. Pretty good. I have fairly normalized data. Let's go ahead and try a different image, say an Arctic fox. I'm going to pick that one up, and boom, we've got an Arctic fox with a probability of 100. I'll tell you, in real life, 100% is fairly rare, but for the sake of this data set, you can kind of get a sense at that. So my model success of 96.3% in precision basically means of the times that I try to predict a polar bear, I successfully guessed that 96.3% of the time. Pretty good. Or put to the inverse, about 3.7%, I have a false positive, or a picture was actually an Arctic fox, but it should have been a polar bear. Recall just happens to be the same number in this context because it's a simple model, but it's basically measuring the total number of trials, basically the ability to predict all labels across polar bear, Arctic fox, and walrus. And average precision is ultimately a more advanced method of that basically seeks to basically remove bias from different dimensions in the data. That's a little advanced for us, but you can kind of look it up in the lab as well. When I'm done with my model here, I can actually publish the model and basically call that model to an API with my prediction key. And so this basically becomes the part of the code that I'm going to use to build my polar bear tracker. All right, are you with me so far? So we have a model, we know how to call that model, and so now we're going to build an application to do that. To do that, I've got to go to Microsoft Azure. And I want to make just a quick plug. If you're a student here, you can build this lab with Azure for Students, which is our free trial. You can see here, I've had this demo running for maybe about 3 days now, 2.5 days, and I've only spent $1 building it. And that's across my SQL server and my serverless function and my blob storage and all of that stuff. So you can do a lot with this. So what I'm going to do is first show you how I generate my cameras. And what I've done is I've created a JavaScript app that basically just simulates actual cameras that are in the Canadian North. So node run.js is the script, and basically that initiates my 10 simulated polar cams. And the script is basically generating every few seconds an additional image that is generated from the camera that's being sent up to the cloud. These images, and I'll come back to this script at the end and you can see how this continues to run. All of these are then uploaded to my blob storage on Azure, and that's really what these images are that you see in the screen here. So let's just say image 4 has a little bit of metadata that is attached to it. You can see now that data has latitude and longitude. It was identified from polar cam number 10, and so on and so forth. So this is real data of when it was modified, when it was created, and so on. And then I'm going to write some code in the cloud using Azure Functions. What's really cool about Azure Functions is basically I don't have to set up my own environment. All I have to do is grab that blob image that I stored, write a little bit of logic to be able to call that blob into Custom Vision Service, and then I'm going to write that to a database to be able to visualize it. The really important part about this code is my request is basically the code that I'm not showing above the screen because it has my username and password. And that request is then basically then being sent to Custom Vision Service through the prediction URL. That was the URL that I showed you in Custom Vision, and the key that basically entitles me to be able to call that API and get some type of output. The other really important part about this code is that I want Custom Vision to return a value to me. And in this case, if the probability, or for probability, that is a polar bear, that is, pull me all those images that are polar bear based on the model. And in every Custom Vision model, all values are assigned a confidence score. That is, I think this is a polar bear, and I'm 60% confident in that guess. Or I think this is a fox, and I'm 70% confident, and so on and so forth. So in this case, basically, what we've done is we've said 80% is the threshold that we believe is the right indicator of a polar bear. And so pull me that, write it to the database if that probability is over 80%, is greater than 80%. For the sake of time, I'll show you that we have a database here that then stores that data. But then probably the most interesting thing is Power BI, which allows us to then visualize that dashboard. Looks like when I switched my screen, Power BI crashed on me here, so I will go ahead and set that up and try to log in real quick. And if that takes too long, I have a nifty slide, because when you're giving a demo, always have a backup. All right. I'm going to wait for just a minute because I really want to show you this. All right, here we go, up and running. So here is my polar bear tracker. You can see I'm on Cornwallis Island. And based on my computer vision model, we have guessed certain locations that return the value that the polar bear is true, that denotes the green, and other wildlife like foxes or walruses return as false, that is red. And I can explore this. I can pick only those polar bears that are true and kind of zero in on the particular polar bears there, or maybe I can explore a particular camera and learn a little bit more about metadata around that as well. And so that is my polar bear tracker. Pretty cool. You can build this yourself. And you can see here, this is a real live map. So I'm scrolling out, and there is the Canadian Arctic, where we are. Very cool. So let's go ahead and close off with a couple more things. So why does this matter, right? Beyond, let me switch over from display mode there. So why does this matter? So we can do amazing things with computer vision. Not only can we build polar bear trackers or just classify polar bears, but we can actually classify any number of species on the planet. And this might be quite interesting if I were, say, on the African savanna, and I wanted to be able to track different animal migrations or uniquely tie that. What if I wanted to track individual unique animals, maybe identifying by the whale's tail fin or the spots on a cheetah or a zebra or whatnot? We can actually get to that level of precision with computer vision. Pretty amazing stuff. So closing this out, again, climate change won't wait, so do it for them. If you want to build this yourself, aka.ms/polarbearmodel. So thank you, and we'll go ahead and move to questions.
So hi, Justin. Some great questions. So one from one reader was, how do you actually understand what the image is? How does custom vision start to understand what the image is?
Yeah, that's a great question. The answer is fairly complicated, but I will summarize and maybe send a link after as well to go into more detail. So basically what we're doing is we're transforming an image into a set of mathematical values, an array, if you will, that a computer vision or that a computer can basically understand. So if you think about, let's take a pixel on my shirt right here that is blue. That is assigned red, green, and blue, an RGB value, and that has 3 codes that indicate what that unique color is. Well, those 3 values can actually become an array that indicates that pixel. And so if you put together all the different pixels in an image and you align them in sequence, you can actually have an array within an array. And that mathematics is what allows a computer vision model to then interpret all that data and then match that. So when we say computer vision, the computer is not actually taking a look at an image in the way that maybe our human eyes, the way we interpret is. What it's really doing is it's converting it to math that it can understand and then employing mathematical algorithms to then evaluate that versus other images that have also been converted to math.
So another great question, Justin, was, do these computer vision models get better over time with the help of machine learning?
Yeah, it's a great question. They do tend to get better over time according to the type of training data. But there is actually some situations in which you can make your model worse. That is why trial and error is so important. There is the concept of oversampling data or bringing in too many features into a data set. So more is not always better. And let me give you an example. So the images that we trained in this model were ultimately fairly small images, really only 30 pixels by 30 pixels if I recall, but something fairly small. And that was to make it computationally efficient for the computer to interpret. So pulling in, say, a 4K image and evaluating thousands of 4K images might not actually be the best approach versus normalizing your data or simplifying or performing other data science operations to make that more readable for computers.
And another question is, what if I have a ton of images and don't want to store the images as a blob? Is it possible to have just the data as metadata base, and can I interact with that in real time? Interacting with a database in real time, yes, that is possible. Blob storage is just a simple way to store images because it's unstructured data. If you're trying to store your data in a more structured or relational database, there's other operations that you have to take with that. So in this exercise, blob storage tends to work quite well, but nothing that I'm aware of would prevent you from using data from a relational database as well. Excellent. So another question, I think this is actually from InstaFluff, which is a great question, is around how do you build online and offline models? You know, so at the moment, everything is online that you've shown using custom vision. Can you take that offline if you don't have an internet connection? Yeah, that's a fantastic question. I think, Lee, you're actually more expert on building on the edge than I am in that one, but I will venture an answer, and if you want to follow up, that's great. I say that because Lee has a session coming up too and is also doing some great work with Oxford, where we're doing edge computing as well. So edge computing is basically the concept that you can take a machine learning model
that would be online, that is connected to the cloud, and deploy that model offline, that is directly on the end node. So in our scenario, that could be with the camera or the small computer, the Raspberry Pi, where the model has been deployed. The reasons why you might do that is because it's more computationally efficient. You don't have to stream to the cloud. But some of the maybe the downsides to that is that you still have to collect the data at some point. So there has to be maybe the model processes the data and only the output of that is then sent to the cloud, which makes it easier for scientists to analyze without having to process that in the cloud each time.
Excellent. So just as a final question, is it possible to export models from custom vision to Onyx, or do we have to train them differently? So again, do you want me to answer that one?
You know, I am not sure if we allow export to Onyx. I don't suppose if you know, Lee.
Yeah,
but,
we do.
But
yeah. So we do support export to Onyx, and we also support export to TensorFlow Lite. So again, that works directly from custom vision. You just do export to local model.
Yeah, very cool.
Great. So thank you, everyone, for the questions. I think we've had a great session there. Just a huge thank you to Justin, and a huge thank you for all you for joining us from all around the world. And I hope this session's been enjoyable and you've had some great experiences. So enjoy the rest of the build.
Yeah, thank you. Have a good day.